Tomorrow we have an exam on electrodynamics, and I figured we'd best make a video to do a little bit of review. I think that the most important concept in this session is going to be understanding how to use this Laplace equation. And it's probably important to figure out how we derive the Poisson equation from, this is just Gauss's law right here. Sort of another way to write Gauss's law is this, you got E dot dA, but it also just could be written like this, divergence of the electric field. And if you remember that the electric field is just the negative of the potential, negative of the gradient of the potential, then you plug that in there and, well, you just basically get the Poisson equation from that. And if you figure that the charge density is equal to zero, then you get the Laplace equation from that. Just remember that the charge being equal to zero does not mean that the voltage potential here is equal to zero. It only means that the density is equal to zero. So basically, you could have a constant voltage on the surface of your conductor. This is all about conductors and like kind of how charges work in the region of these conductors. And if you have the voltage on the surface, then you're actually going to have the constant voltage of that potential inside the conductor as well. So like, there's different types of conductors. I suppose you have a cylindrical conductor or a spherical conductor. These are kinds of the things that maybe even a plane. But anyway, so inside a conductor, we always know that the electric field is equal to zero because charges like to distribute around to cancel the electric field inside. And on the surface, I think we have a perpendicular electric field that's going to be this surface charge over the this epsilon naught constant. So that's all pretty interesting. Um, Now this section is really all about like how potentials act around various ways. So the classic way to think about the potential is this point charge method, where if you just have a point charge, it's like Q divided by R, um, and then you have the electric constant in front here. This is another way to write it with these weird um, vector method. Let's not worry too much about that, but you can think about like here is the radius, and then here is the point you're trying to reach. So it's like the point minus the radius that you're at. And then this makes this little vector fancy R. And so fancy R is basically this way here. We could do the point you're trying to reach minus the radius you're at, and then you get the fancy R vector. So it's great. We can manipulate this fancy R vector in various ways. As you can see, we can find the magnitude by taking the square root of the dot product. Take the dot product and you get this long thing. It's pretty important that you can find the magnitude of two vectors, like the square of two vectors, and you subtract them, equals r1 squared plus r2 squared minus this 2r cosine the angles between them. So that's pretty important. Now, if you're trying to find multiple charges in various places, you have to sum up these point charges. And one classic way to have to sum up point charges is because of infinite charge images. That's a problem. So let's take this Q that's right here in the middle, and let's figure we're going to have these two planes that are conducting planes. It might be grounded, it might be conducting. I'm not exactly sure what these planes are all about. I think they're grounded planes right here. So voltage is essentially zero at these surfaces here. V is zero, zero potential. So if we're trying to get these boundary conditions, we have to cancel the charge. If this is a charge of zero, then we have to basically take this Q and this other negative Q, add them up, and then right here we get zero potential. Same thing over here. The only way to do that was to sort of throw in these negative image charges that are going to enforce that this region here is zero. Like that's the only way. In fact, there's this uniqueness solution over here that it says that if there is a solution that satisfies uh, these Poisson equations and the Laplace equation and the boundary conditions, then it's the only solution. It's the only way that we could possibly make this thing here zero is to have a negative charge exactly the same distance away. There's no other way. Okay, So that's interesting. Now, of course, if we're thinking about the q's, we think qn because there's infinite of these, right? So we take -1 to the power of n. We can sort of figure out what the charge is of that particular q that we're counting, and we have to do this little sum over the n's. And this rn over here, the rn is just kind of like if you're doing in the z direction over here. Um, right, this is the z direction. -z direction. But here you're doing something like x squared plus y squared plus z minus zn squared. And that will give you all of the potentials for all of these little charges. Just like that, nice and easy. It's not too crazy. You can even figure out what the force is on this particular charge if you were to calculate that you have another charge, the distance of 2d away. This is 1d, this is 2d. So then you have to just multiply the two charges, considering that they're 2D apart. And if you want to do like a sum over that, you could also do a sum over all this. So, actually, I'm not too sure if you have to do a sum. You might have to do some weird thing with these with the distances. So that might be a little bit confusing there. But yeah, so gets very complicated very fast. So, we're just trying to keep things, I guess, as simple as possible for a moment. So we kind of deal with the point charges, we deal with infinite charge images, um, and now let's consider, oh yeah, so you could also have ch image charges for the sphere, and this is really important. Um, so, you have a Q over here, and you're thinking, how many image charges are there inside the sphere? Well, we have to figure out, take a negative q, okay? So we have positive q outside, we're going to need a negative q inside, and then we're going to have this sort of a ratio between the radius that we have, the r, and then the distance that we're away from it. So we kind of want this little ratio, and this distance is going to be position of the external q minus the uh, the center right here. So you kind of just do this little distance calculation and you can get your z for where these charges are right here. Z for the charges. Um, so you take the center minus, um, this is z here for the charges. You take your center minus the r squared over this distance here. I guess this distance has absolute value right here. Cool. All right, so just these three equations will help to figure out where all the charges are inside of an image. Sorry, where all the image charges are inside of a sphere. Just plug everything in here. As long as you know the z external, which is the position of this q, I think, um, and then you can find the center. And I mean, these other values are pretty easy. And you kind of have this little sum here where you have the v out. I think we might have to do like a sum. And here's the r. Same thing that we did before, right? And I'm not too sure what this is here. What's the Bessel function? This is like separating stuff, which we might have to take a look at in a second. Yeah, so this is separating equations. So basically, a great way to solve this Laplace equation here. It feels maybe like we're jumping around a little bit, but I don't know. So solving this Laplace equation is pretty important. Uh, but I think we wanted to come back to that a little bit later. Let's go back over here to what we're doing with the image charges. And I think there's one thing we need to focus on first. It's like these boundary conditions because you're solving for these weird potentials in places, and in order to get the equation for the potential, you have to solve the Laplace equation. So, but once you get the equation for the potential, I mean, heck, this is an equation for potential. What do you do with it? How do you enforce these constants and like figure out what the actual, like this is a general equation. There's no constants and no exponents plugged in. So how do you actually find those constants? You have to consider the boundary conditions. And this is probably one of the biggest, most important parts. So let's start with it. In fact, there's only three types of boundary conditions. Um, I'll call them categories because there's a lot of different. there's a category A right here. Category A is basically limits. So here's the limits. You could go from negative infinity, positive infinity to zero. You definitely want to have a finite origin when r goes to zero. So when you plug r equals zero into your equation, like say you plug r equals zero over let's plug in an m equals zero here. Where do I get a good equation for this? R equals zero. Give me a second here. Find a good situation for this. I mean, consider like this term here. So, if r consider this term. If r goes to zero, then this term just becomes zero. If r goes to infinity, that term also becomes infinity. Same thing here. R goes to zero, this term becomes infinity. If r goes to infinity, this term becomes zero. This is 1 over r squared. So you just want to enforce that constants like drop out or become zero if the equation doesn't make sense anymore. Like the voltage can't blow up. So if the voltage ends up going to infinity, then the constant that's causing that is going to have to be equal to zero. And we could also do the same thing with the infinity. So if you try to move out to infinity and there's a term in your equation that is causing the whole thing to go to infinity, then the constant has to go away. Like say over here, if you plug in r here, it goes to infinity, then this term becomes infinite, and that doesn't make any sense. So therefore, a must be equal to zero to get rid of this entire constant. That's kind of just a confusing part of this situation. I didn't really have an example written here, but these are just little reminders. And then the next thing we have is boundaries. And I guess I'll switch these two because this is kind of the third type of boundary condition. Something like this. Switch that over here. And so we're looking at the boundary conditions B. I guess I'll call them surfaces. B is all about surfaces. So there's two types of surfaces, one that has a charge on it, so the potentials have to match. If you got the potential in two different, get two voltages split apart, and there's like a surface in between them, then voltage has to be equal for the two fields at that surface. Okay, and then so the voltage can be totally different on this side and totally different on that side. But at that surface, the connection between the two is going to be equal. So you just have to set them equal, like at R equals R. Those two voltages are the same. And that is the second type of boundary condition. It could be zero, of course, so this would be another way. It's grounded bounded surfaces or charged surfaces. And then the third type is the electric flux. So call this C, and this is the flux. This is like a Maxwell boundary condition, they call it. The idea is that the electric field inside minus the or outside minus the inside is going to give you the Gauss's law. We have the surface charge density divided by the epsilon naught. This becomes the derivative of these voltages, but in the ideal conductor, En equals zero, so this potentially could go away, but you might have to deal with like plugging in R's at particular things and finding out what the flux is. So there's kind of like three different ways to take these boundary conditions and apply them to the potential. So that way you get the accurate equation for like 3 different points or 5 different points, all the different types of positions around that voltage that you're looking at. All right, here's something a little bit about multipoles. I think this is useful for when you're like really far away, then these things kind of reduce to some sort of approximations here. Although this is kind of a confusing topic and I don't really get it too much. This dipole right here is going to be like p cosine theta divided by 4 pi epsilon r squared. I think this is just a voltage potential for a dipole moment when L equals 1. And here is what P is. It's just the charge times the distance between them. And finding some interesting equations that might help to solve this. If you have a monopole plus a dipole. So that could help. Um, let's see what else we can do here. Central force. This is a little bit weird. Get that too much. Now, yeah, so basically, let's consider the solutions are for a cylindrical, it's like the solutions for every single Laplace equation in cylinder form and in spherical form. So here's the cylinder form. It's going to be the simple thing, am r to the m, r to the negative m, and then you've got like cosines and sines. This is in cylinder form. I think that we have to assume, though, that we have this a, b, x. We're assuming like this voltage boundary conditions, I guess. In the spherical form, we have this, which leads us to the Legendre polynomial functions. But again, this is just two different ways to find solutions for the Laplace equation. And here are some applied boundary conditions. Like again, here's r going to 0 means that BL equals 0 because r is actually in the denominator over here. Notice there's the next negative exponent. So if r is on the bottom here, then this whole term would go to infinity if this was going to 0. Therefore, we must drop it. Reverse for this one right here. So let's walk through a quick way to solve the Laplace equation. Notice what we're really doing with the voltage. We're taking a double derivative, essentially. And we're getting this fxx plus fyy plus fzz. So we split that apart, and then we divide it by v, and we get to this thing here. We get sort of second derivative divided by a, second derivative divided by b, the second derivative divided by c there. These are all constants. And then we can sort of separate them out like this in sort of like negative kx squared, negative ky squared, and kz squared. And then we can get solutions to those. Let's drop down over here, skipping past these basic equations for gradient, divergence, curl, and Laplace. And look at the Laplace differential equations here and sort of all the solutions that we can get if we're in spherical form, cylindrical, or Cartesian. Well, this is the basic Cartesian form. So usually, you get a solution in terms of sine waves or exponents here. It depends whether you have a plus or a minus sign for your two. It's like the most basic differential equation solution, simple harmonic motion, etc. You get these two equations either with the imaginary exponents, which simplifies to sines and cosines, or the not imaginary exponents, real exponents, which signify decay or growth. So those are a possibility. This one is for the negative. You have real exponents, and this one is imaginary. You have positive right there. Same thing would happen in cylindrical coordinates. We kind of get the very similar thing happening with the azimuth here. It's just a basic simple harmonic motion, and the longitude, even plus or minus form. But on the radial side, we have this Bessel function type of thing showing up. Where you have this type of equation being a solution. how do we get to this form? Remember, we had to do all this right here, and when we separate it all, we kind of get different equations. And one of them, in cylindrical form, is this one. And once you get to this form, by sort of reducing the voltage and playing around with it and separating it out and getting these constants all lined up, and you see that the voltage turns out to this, and like this could have been one of the A's, A double prime, or it could have been B double prime. You know, I think this is probably matching A, B, and C. And so your A equation would match this form, where your B equation would match this form, and your C equation would match that form. Okay, you kind of line it up like that, because you're matching A to the R, you're matching B to the azimuth, and you're matching C to the longitude. So then in this form, when you solve solution A like this, it comes to this form, and then this is the answer. It's just the Joker function. The Joker and the Yoker. These are the Bessel functions. They're a little bit kind of advanced, so like you'd probably be asked more to solve these two rather than the Joker functions. Those are a little crazy. But in spherical form, it's a little bit easier. So, you know, your A would match to the radial, which actually becomes a Cauchy-Euler. As you can see, this is the form of the equation that voltage reduces to, or the A part of the voltage. This is, I know I put it in terms of R here, but this would be like A double prime, A prime, and A. And what I mean by A is, again, we went up back here. We assume that the voltage is A, B, and C. So, you know, your solution for A, this is like the radius side, this is the azimuth side, and the z side. Back over here. So we got these three that we're looking at in spherical. We have the Cauchy-Euler's, the first form. Just you get two different kinds of answers, one for m equals 0, one for m greater than 0. You get the Legendre in the polar. So this is probably the hardest one because you have a really complicated form over here. But we'll talk about that in just a second. And then we have the azimuth again, which is a pretty simple one, which just reduces the simple harmonic motion. Now for the Legendre polynomials, this is like the solution to this equation. You get this, and you're like, oh, I know the solution. It's this, one of the polynomials. Um, so you kind of have to figure out whether your solution is going to be just like a constant, or whether it's in terms of cosine, or whether you have a cosine squared or a cosine of 2 theta. And I will tell you which L to use. And now, besides that, it's kind of too complicated for me to really explain. I have no idea how these things work. It's just kind of a little bit insane. But I know the reasoning behind it. The idea is that if you would to solve this equation here, up here, like the solutions, like the Legendre equations tend to pop out of this. Like, let's say here's the way we can do that. So in here's the Laplacian in spherical, and then we're considering the case when all this uh, azimuth stuff goes away, and we're doing it only in the r in the polar direction. The solution here is essentially for the polar direction, right? So the r kind of goes away. But so if we do this, this turns out to be something like r prime divided by r. This thing turns out to be something like theta prime divided by theta. But notice that these coefficients in front, this one has r squared over here inside. This one has the sine of theta inside. Then we got rid of r squared because we multiplied everything by r squared. And since zero's on this side, we can do that. But here now we have sine of theta in the denominator. And sine of theta in the denominator is a very big problem because As soon as sine of theta goes into the denominator, the solution to this equation becomes weird because you have to avoid dividing by sine of 0 and sine of pi. Because of that, all the solutions have to be cosines. So that when you get cosine divided by sine, you get some tangent or something, or cotangent. I think that's how it works. But yeah, the idea is that there's a sine theta on the denominator here as we try to solve for this. Notice how we were able to set this term here on the left to be a constant, this term on the right to be a constant. They're both constant, they have 0. This one is L plus 1, this one is minus L plus 1. So that way they both cancel out to 0. Um, that's kind of a different story. You know, the idea again, the reason we have cosines in the Legendre polynomials is because we were trying to avoid dividing by sine of 0 or sine of pi. And why is 0 and pi important? Well, remember the polar angle itself goes only from 0 to pi. So those are the limits of the polar angle, and you kind of just have to avoid those limits by using cosines. So that's kind of interesting. That's how we kind of got the Legendres out, and the azimuth again was just like a simple harmonic motion. So it kind of gives us a lot of information that we kind of have to use these voltages to solve for these different forms and figure out what the solution is to all these voltages. Wow, it's a little bit intense, but I think that kind of covers most of what we were doing here. So hopefully that was somewhat helpful. And yeah, thanks so much for watching. Y'all have an awesome day.